So it's important for us to monitor the effects of acid deposition. And we can first classify our acids in two different ways. One is quantitatively, which involves measurement. So we can measure the pH of an acid, um, and we can do a titration of an acid. Or we can measure qualitative things, and this involves properties such as characteristics and attributes that we can observe with our five senses. So a titration is done to determine the amount of acid or base present in a sample. So we use an acid, base, and an indicator. The end point is reached when the indicator changes color, and then the amount of acid or base needed to neutralize the solution is known. So we have an unknown sample in the vial, and then in the burette, we have a known concentration of an acidic or basic solution, and then we measure the volume of that solution, and then we can calculate the concentration of our known volume of the unknown solution in the vial. So when we're calculating concentrations, we calculate this in moles per liter, and we also want to use our volume in liters. So the formula in your textbook or in your data booklet given is concentration is equal to moles per volume. So calculate the concentration in moles per liter of a 250 milliliter solution containing 0.243 moles of potassium hydroxide. So this will be a basic solution. And this is going to be used to analyze the concentration of an acid. So we're given moles and volume and 0.250 liters. So putting that into our equation, we have a concentration of 0.972 moles per liter. So the potassium hydroxide has a concentration of 0.972 moles per liter. Now the concentration of the acid could be changed by adding more solvent. And what would the concentration of potassium hydroxide be if we added another 150 milliliters of water to the solution? Okay, so we're going to take the same formula, C equals N over V. And we're going to keep our same moles of solution. Our moles is still going to be the same at 0.243 moles, but now we're going to divide it by 0.400 liters because we've added 150 milliliters to the solution. So 0.243 divided by 0.4 gives us a total concentration here of 0.608 moles per liter. That's a zero there. So 608 moles per liter. So we've made a more dilute solution by adding more water. Now we have a couple different types of equations that we can do here if we want to do a titration analysis. So in one, we have a standard solution where we know the concentration and volume. And then we have an unknown solution where we typically know the volume, but not the concentration. And these acid-base titrations involve a neutralization reaction. So our known might be an acid and our unknown might be a base, or vice versa, because then we can see the change when it neutralizes. So the solution with a known concentration goes in the burette tube so that we can measure its volume. The sample with the unknown concentration goes in the Erlenmeyer flask. So we know this sample's volume, but we don't know its concentration. And the titration process, we're going to add that titrant solution drop by drop until they've fully reacted. So there's an equal amount of acid and base depending on their molar concentration, and this is the end point of the reaction. So we know we've reached the end point of the reaction because the Erlenmeyer flask is going to, the fluid in the Erlenmeyer flask will change color when we've reached the end point because we've added an indicator. So the indicator changes color at the end point because we've changed the pH sufficiently to reach that stage. When we're reading the volume of titrant on the burette, we want to read this volume before we've reached the endpoint, like before we begin, and then once the endpoint has been reached. We're going to subtract the difference between those volumes to get our total amount of titrate used. And again, we want to read the bottom of the meniscus for our starting and finishing volume. So we're going to calculate the moles for the given substances. Then we can use a molar ratio to calculate this. So make sure we use the appropriate calculation for the question you're asked. So find the concentration of a solution of potassium that requires 8.32 milliliters of a 1 mole standard solution to neutralize a hydrochloric acid solution that's 10 milliliters. So to do this equation, we're going to use the formula C equals N over V twice. So first, we're going to calculate the solution of the moles in the solution of hydrochloric acid because we know our volume. And so C equals N over V. So to calculate the moles, we're going to go moles is equal to concentration times volume. And we're going to do this for the hydrochloric acid because we know both its concentration and its volume. So it's a 0.100 moles per liter. We're going to multiply this by 0.00832 liters. Gives us a total moles of 8.32 times 10 to the negative 4 moles. Now, this is the moles of the hydrochloric acid. Now, when we look at our balanced reaction, we have 1 mole of hydrochloric acid balances 1 mole of potassium hydroxide. So we can carry this over into our next equation. So now we're going to go concentration is equal to moles divided by volume for our potassium hydroxide. So we're going to take our 8.32 times 10 to the negative 4 moles per liter, or moles, divided by our volume of 0.010 liters, and we get a total concentration of 0.832 moles per liter. So we use that formula twice, once to calculate the moles of our known solution, and then with our balanced chemical equation, we knew that that was valued at the same as 1 mole of potassium hydroxide, so we were able to calculate the concentration of that solution. So when we're looking at acids and bases, strength does not equal concentration. Strength refers to the percent of that acid or base that dissociates in water. So we can't change we can change the concentration of an acid or a base, but we cannot change its strength. So strong acids and strong bases dissociate completely in aqueous solutions and they become strong conductors. And weak acids and weak bases, only a portion of that acid or base molecule becomes dissociated in water. So some strong bases are sodium hydroxide, which dissociates completely in water and becomes sodium molecules and hydroxide molecules. Acetic acid is a weak acid where most acidic molecules do not release protons but remain in the undissociated form. So they'll be still as acetic acid molecules. So for every weak acid, there's a conjugate base. And what's going to be the conjugate base of acetic acid? So the conjugate base of acetic acid is going to be the CH3COO negative. So that's the acetic acid after it's donated its hydrogen ion. When it comes to acids and bases, we also want to talk about buffers. So a buffer is a weak acid or a weak base conjugate pair. So these are ones that don't dissociate, so the pH doesn't change a lot. And it's most effective when there's equal amounts of acids and bases. So for example, we have H2CO3 in the blood. So CO2 and H2O react to make carbonic acid, or H2CO3. And carbonic acid is going to resist changes in blood pH. So we have carbonic acid and H3O positive. We have a slightly acidic molecule and a slightly basic molecule. So that pH in our blood is not really going to change. So when we look at sources of buffering in the environment, these include hydrogen carbonate in our blood, levels of carbonate in the soil, and limestone deposits. Buffers don't work forever, though. They only resist the change in a pH. So in Eastern Canada, we've reached the capacity of the soil to buffer itself, and the acid deposition is currently changing the pH of the soil in that location. So here we can see a buffer in action where we have the resistance to a change in pH until we reach a certain point and that conjugate acid is exhausted, and then the pH can swiftly increase. And we can see the opposite on the other chart where that with the amount of acid changing, we don't see a great change in pH until all of a sudden we've resisted we got to the end of the buffering capacity, and then we have a drastic drop in the pH. I hope you enjoyed today's lesson. Take care.